Good morning, folks. So here we are, Monday, October 26th. This is the last week of our organic molecules unit. We will be testing out at the end of this week. And so starting off for these first 2 days, I really want to go over probably the most important part of this entire week. Today, we're going to be working with and talking about our enzymes. So if you don't remember what enzymes are from previous years, that's just fine. And instead, what we're going to do is we're going to roll through a little bit of an intro here, So we are in week 2 of unit 2. So once again, if you go back and you were to look at the whole Schoology, we are in unit 2, the biomolecules. We are in week 2, enzymes. And this PowerPoint that we're going to be going into today is actually the exact same one that we started with last week. It's the exact same file. We're just going to be starting a little bit later in it. Last week, we went over our 4 organic molecules: carbohydrates, lipids, nucleic acids, and proteins. We talked about what their uses were in the body, what they look like, their monomer and their polymer, all of that stuff. Now we're going into a very particular kind of protein, the enzymes. So when we open that up, we left off with this slide where we were taking a look at the complexity of the shapes that proteins can make. Remember, everything about a protein is determined by its shape. If its shape changes, that is going to change the job that the protein can do. That can be a very real problem. So our enzymes themselves are going to be the super important type of protein. All right, inside your body, you have 4 quadrillion chemical reactions, all occurring every second that you're alive. If too many of those go out of control, we have very real problems, life-threatening problems, right? All right, maintaining those, that's that homeostasis we talked about last unit with our 8 characteristics of life. And so enzymes are our control mechanism. And that's because they are what we call a catalyst. Catalysts are going to be any substance that can speed up the rate of a chemical reaction. And it's going to do this by saving us energy from the reaction, which is amazing. Would you rather spend $20 for something that you have to buy, or would you rather spend $10 for something that you have to buy? These chemical reactions have to happen or we don't live. So the question is just, how much energy do we want to spend? And if you have a coupon, an enzyme, that gives you a discount on that energy, that's a good deal. As a matter of fact, we could not survive without them. Without our enzymes doing their job, we could not survive. You could not eat enough food, digest, and circulate it through your body in order to provide the energy that you would need to keep going. So, super important. Now, this is the most common way that they're referred to, and that is by what we call a lock and key model. And really, the only reason that they're doing that is because they want you to think about it kind of like this car key, right? It's going to be real good at its one job. It is shaped just right to fit into the lock in order to start the car, to open the doors, things like that. Now, I can have other keys, and if I try to use this key to do something similar, it's not going to work. It's not the right shape. When we look at enzymes, it is all about how specific they are. They are designed for one another, quite literally. So the enzyme and the key, what we call the substrate, must fit together. Now, this is called the active site, and the active site is this special region of the enzyme that is shaped to fit the substrate. As long as it is the right shape, the substrate will bind to it, like you see in the second picture, and then that's going to weaken and break the substrate down into what we call the products. The enzyme will then go on to do this again. Now, it doesn't really look like this top picture, but this bottom one is much more accurate for what we would see. Either way, the idea is the same. The shapes must fit for the reaction to take place. This is what the energy cost would look like. That's the red line here without enzymes. The blue line is with enzymes. Now, this may not be true for every single reaction in a human body, but they do reduce the energy requirement in every reaction in the human body that they're a part of. So you can see here with this example, it's about 1/3 the cost that it would be otherwise. So once again, the difference between paying $20 or $7, which one is preferable? There are some ways, though, that we can affect how enzymes work. The first one of them is temperature. So as we start to heat up an environment, here's the temperature along the bottom. You'll notice it's getting warmer. Enzyme activity is on our y-axis. And so as we add heat, you'll see the enzyme activity goes up and up because we're adding more energy into the system. Molecules are moving around faster, so they're colliding with each other. More reactions are happening. But we hit this point, this optimum temperature, where this is the best the enzyme can work. If we go above that, then you can see the enzyme's activity starts to drop off. This is actually one of the major reasons why you'll go to the hospital if you have a super high fever. It's not that we can't survive those temperatures. Clearly we can. You guys can go outside on a summer day when it's 110 degrees without being afraid of falling over dead. Like, we have mechanisms to control that. The problem is when your internal temperature starts to go that high, your enzymes are not designed to work at those temperatures. And so we see your enzyme activity start to drop. Now all of a sudden your body is requiring more energy to do everything, and that could be a very serious issue. So we want you to get to a hospital to try to get your temperature under control and cool down so that more systems inside don't go haywire. So temperature can absolutely cause a problem because it's like taking a blowtorch to a key. If we add enough temperature to this key, all these edges, all these shapes are going to start to melt. They're going to change. Then the lock doesn't fit the key. The shape has changed. The function has changed. The enzyme cannot work. So it's a pretty easy thing to remember. Second, we can change the concentration, namely of the substrate. And this one's less important than virtually all the other ones. It does no lasting damage to the enzyme. All we're saying is that eventually you hit this point where the enzyme just can't work any faster. The example I tell people in class is, imagine your favorite food in the whole world, plate in front of you, right? If I put 5 servings of your favorite food on that plate, and you just, you haven't eaten in like 2 days, you just dig into that and just stuff in your face. If I start adding more and more servings on there every second or every 5 seconds, chances are you are not going to speed up in eating. You're already going to be eating as fast as you can because you love this food and you haven't eaten in days. So you're already just stuffing your face like crazy. For me, it'd be Doritos. God, I love Doritos. Anyway, the point would be that you just can't go any faster. It doesn't matter how much more food there is for you to break down. You're already at the maximum speed you can go. And finally, this is the second really important one. The first one was temperature. Now we have pH. Now, note, if you don't know this, pH is a measure of how acidic or basic something is. And we'll be going over pH in detail in a little bit. But Understand that whether it is high or low, whether it is basic or acidic, it's going to be bad. Most enzymes only work well in a very narrow range where it's designed for where they function in the body. If you go outside of that range, their activity drops off real fast as the extra acid or base, once again, changes their shape. So here are three different enzymes. We've got our pepsin in blue, which works down in your stomach to digest protein. Notice it works best at a pH of 2, super acidic, really, really dangerous levels of acidic. The moment that the acidity starts to go up towards neutral, which is around 7, it drops off. Salivary amylase is in your mouth. That's what breaks down starches. Notice that one works from 5 to about 9 with its best at neutral, which is 7. Makes sense. You don't want your mouth dripping caustic acid, so your mouth generally is not super acidic. And then there's stuff like arginase, which is an enzyme that helps to break down fats and oils. And notice that one works best around 9.5 to 10 on the basic range, because this is just after the stomach, after you have a whole bunch of other digestive organs pump basic material in to neutralize all of that stomach acid. Well, that's where arginase works. So all of these enzymes have a very particular pH that they prefer. If you go above or below, they're not going to work as well. And that is because temperature and pH will both denature. We saw this once when we were talking about proteins before. Now we're using it specifically to talk about enzymes. So when you denature an enzyme, you are changing the shape of the enzyme so that it will no longer function. Here is what the enzyme should look like. There's the substrate. They should fit together really nicely. But if the heat is above, in this case, 40 degrees Celsius, then now you can see the enzyme has changed in shape. The active site is not the same shape. So now the substrate cannot bind to it anymore. So this is really that key idea. Out of those three conditions, you have to understand that temperature and pH will denature our enzymes and incapacitate them. It will ruin their ability to work. Now, beyond that, we are going to be going into a worksheet today, and we're going to be starting a lab today. I'll have a separate video for the lab coming up, but I do want to show you the worksheet real quick. So the worksheet is very, very simple, but it's practice that everybody should get. Now, hopefully by this point, that's no problem. You can take care of it. Here is your picture and your file. I am not collecting this. This is not a graded assignment. This is something for you to make sure that you can do what you need to do. And on this, you should be able to label and define the enzyme, the substrate, the active site, and the products. So you go back up to this picture here. You want to label what is the enzyme, what is the substrate, what is the active site, and what are the products. And then down in this area, define them. Explain what an enzyme is, what a substrate is, what the active site is, what products are. But the products one I'll help you out is just whatever is at the end of the reaction, whatever the reaction makes. So that should be your practice based on all this enzyme stuff. But if that's not enough, yes, I know I'm presenting. I also included this enzymatic game. So if you go to Bioman Science, they have, I use the term game in the loosest terminology that I can. But it does go over all of the important parts about an enzyme, how they're built, how they work, and then it has these relatively simple little games for you to simulate that. So that's there as some additional practice if you feel that you need it. I hope that this helps everyone understand enzymes at least a little bit better. And with any luck, we'll all have it by the end of the week. Have a great day, and I'll see you soon.